See, I remembered to do the recording. Right, and off we go. So hopefully you can all see the slides there. Oh, no, you can't because I've not shared. Yeah, you should be able to see it then. Sure, someone will yell if they're not seeing it. Okay, so generative AI. Now, um, there's a lot of people in U3A doing a talk on AI. And most of these talks I've noticed is about how to use the most recent form of AI, generative AI. What I've not seen much in the U3A talks is actually how this new form of generative AI actually works. So I figured that would be a nice hole to fill, if you like, to talk about what happens under the covers. The other reason I'm doing the talk is because everyone else is doing one, I feel a little bit left out. So I figured I must do something on AI. So this is what I thought we would go through today. So kick off with a short set of examples of generative artificial intelligence, a showcase, if you like. And this is so that we're all on the same page about what we're talking about. So that will look at what generative AI looks like to the casual user. Then we're going to roll back a bit and talk about how classic AI works. And we've talked about this before in the bird and animal talk. But this is, going back in time really from the 50s up to the 2000s, how classic AI works under the covers. And we need to start there because the generative AI builds on top of classical AI. And then we'll go on to talk about generative AI, in particular when the Pandora's box was opened in 2017. We'll talk about large language models, a couple of demos, and some interesting bits and pieces, such as, how do you test these large language models? And then we'll have a summary and references. Now, during the talk, from my point of view anyway, it's important that I understand how any tool works before using them. So it's like if you drive in a, internal combustion car, if you know a little bit how the engine works, you're driving along and the 12-volt battery light comes on. If you understand how the engine works, the last thing you're going to do is turn the engine off and pull over and turn the engine off. You're going to keep driving until you can stop somewhere where you can get someone to look at it. If you don't understand how the engine works, then you'll pull over, turn the engine off, and won't be able to start it again. So it's always useful to me to understand a little bit how these tools work, and then you're much more likely to get more out of them, understands their pros and cons and weaknesses, and indeed choose whether you want to use them at all. So that's my thinking about doing this talk. So I'm going to kick off. Oh, yes, sorry. What I wanted to say was, so there's a couple of points in this talk where I feel it's important that we understand a particular point that we're talking about. So I will iterate 2 or 3 points several times and pause to see if there's any questions about that. Anyway, let's go on and have a look at the showcase. So generative AI is really all about asking a question with a piece of text, or what is called a prompt. So when you're using these systems, you type something in and you get a response back. And let me get my pointer up. So what you type in here is what's called a prompt. And in this case, this is a generative AI that I'm using. I've typed in, create a 4-line poem suitable for a U3A meeting about AI. And this is what the generative AI replied with. Sure, here's a short 4-line poem about AI that could be suitable for a U3A meeting. Silicon silver glow illuminates our futures bright as AI learns and grows in this digital light. So first example, generative AI can write poems and stories and such like. And actually, interestingly, if you run the same request twice, you'll probably get a different answer. There's some random elements in this. Another little example. In this case, this is a generative AI which has been configured or set up to convert text to a picture. So create a title picture suitable for a U3A meeting about AI. There's a common theme here. And this is what I got. Very photorealistic, very high resolution picture that came out in a few seconds after typing that prompt in. Personally, I find that incredibly impressive. But if you thought that was impressive, I think you'll be astounded by this. Here's my prompt, text to audio this time. Create a song in a male voice suitable for a U3A meeting about AI. Again, sticking to the theme. And this is what I got. Again, within a few seconds, I got a verse, I got lyrics and a chorus. But hey, listen to this. In a world of wire circuits, where the future meets the past, there's a new creation, a glimpse inside the looking glass. Artificial minds mimicking our own, wondering where the line is drawn, but man needs of their machine is thrown. I'll pause it there, but from a single line, creating those lyrics and the audio, that sounds super realistic. I just find that astonishing, absolutely astonishing. Here's another example. And this one is one that I didn't run myself. This is from a generative AI, which isn't yet open to the public. So this is the demo available. So here's a prompt: the story of robots' life in a cyberpunk setting. Text to video. No music with this one, so I can carry on talking. But this is generating a whole video from just that single prompt. Very 3D, photorealistic. Astonishing. Oh. And here's a final one. And this time we're asking a generative AI to take both a picture of our last meeting, and a text. Describe this picture. That's our prompt. Let's see what it comes up with this time. The image you provided appears to be a screenshot from a video call. Blah. So again, the generative AI is taking picture and the prompt and really described to us the contents of that picture. And you can go on and add other queries, who is the person second on the right, or whatever queries you want to do about the picture. So this is the world of generative AI. You type in your prompt and you get something generated back to you. So that's what we're talking about today. But as I said before, we're going to start at the beginning, talk about classic AI. And this, I suppose, in date order goes back to the 50s and 60s. You can go back there, buy some books that describe all these things. So it's not a new science, but it's certainly evolved fast recently. So first big question is, why on earth do we want artificial intelligence? What's it bringing to the game? What tools has it provided? Well, if you look at traditional ways you program computers, you tend to fall into one or two ways of programming them. You either do imperative or procedural, and where you describe step by step what you want the computer to do. So if you're controlling traffic lights or something, you say, go red and amber, and then go green, step by step. The other way, which is far less common actually, is called declarative, where instead of telling the computer step by step what to do, you declare what you want. So an example might be that you declare a mathematical formula of something, and then the computer will, draw the graph or solve the equation or something like that. But the declarative is very domain specific, shall we say. The problems that we've got is those traditional ways to program computers don't work very well on some classes of problems. So if you think about things like nonlinear problems, where you're separating data from noise, maybe stock market predictions, text classification, such as spam filtering, speech recognition, image recognition, for example, trying to distinguish between a blackbird or a fox in your back garden. Or really general pattern recognition, these traditional programming approaches, they can be used, but it's really hard to get it right. So artificial intelligence, or more specifically in today's talk, a branch of artificial intelligence called artificial neural networks, is a way that we can solve these types of problems without writing step by step on a computer how to try and solve them. And we try to say that artificial neural networks are inspired by neurons in the brain. They're not really copying the biological equivalent. The developers working on these systems are really just getting inspiration from the biological equivalent. So some definitions. So artificial intelligence is actually two separate things. It's the intelligence of machines or software, obviously, as opposed to intelligence of living beings. But it's also a field of study in computer science. And personally, coming from that background, I suppose, I've always thought as AI as being a part of computer science. It's a study, it's a set of courses you go and study and so on. But of course, these days you see in the press a liberal use of AI, and they tend to refer to particular systems rather than the science. Artificial neural network is a branch of AI or machine learning, which is trying to implement AI with a structure which is similar about how our brains work. And then there's this artificial general intelligence. If we get really, really clever with artificial intelligence, they start to become or could become intelligent to work out any potential problem by themselves. So now there's lots of different ways that you can draw this diagram. And I know you've probably seen similar diagrams before, but this is the way I'm drawing it just to support this talk, really. So we've got this whole area of this whole science, artificial intelligence. And within that subject, within that science, we have neural networks. So neural networks is a way you can implement artificial intelligence. You can also, if you were to work in this area, you can also implement artificial intelligence without neural networks, particularly in the long distance. Most implementations these days are using neural networks. Within neural networks, we have classifiers, which are really the older classical style of neural network implementations. And we've got the more modern generators. And some little examples, decision trees like spam filtering on your email box is a form of artificial intelligence, but it's not typically implemented with neural networks. We can have object detection systems like, bird spotting or facial recognitions, which is implemented with neural networks as a classifier. And of course, very recently, we've had this new form of artificial intelligence using neural networks called generators or generative AI, particularly large language models. And somewhere in the middle, we got this thing called general intelligence. So today, what we're going to talk about is we're going to talk initially about these classifiers of neural networks and then gradually sneak over to this more modern generative AI. Hopefully that kind of sets the scene what we're going to talk about today. So I've got a list of people on the chat. So if you want to stop me, just raise your hand, and then we can pause. Right. So we're going to start off with classical neural networks, a branch of artificial intelligence. So we're going to talk about this perceptron, or what I tend to call them neurons. They're also called nodes. You know, one of the irritating things about artificial intelligence as a science, the engineers tend to use different words for the same thing. So it can get a little bit confusing. But we're going way back into the 50s now. You can go and buy a book that describes all this. This is what a single neuron looks like. Okay, so we have some inputs here, x1, x2. We've got some weights. We've got a summation. We've got a function here. We've got an output. Here we are, labeling them. Inputs, weights, activation function. And the output is often called a predicted output, a little bit of a weird thing. Now, the thing is, everything we're going to talk about now is built on this building block. When you go online and use ChatGPT-4, they're built on this concept. So this is really the foundation of how artificial neural networks work. So we're going to spend a little bit of time on how these work, and they're surprisingly simple. So let's take an example. We'll put some numbers in for the weights, and we'll create an activation function. So we're only going to get an output here if 1 times minus 0.8 plus input 1 times 0.5 plus input 2 times 0.5 is greater than 0, then we fire. That is the principal sum how these artificial neurons work. So let's put some inputs there just to hammer home how this is working. Oh. If we put some inputs like 0 and 0 in there, you can do all the sums yourself, and you end up with 0. You put a 1 and a 0, again, you can do all these sums, and you get output with a 0. You put 2 1s in, do the sums, and we get a 1 output. So if you know your Boolean logic, this is a simple AND gate. Not that it matters. And this is it. This is the foundation of all neural network implementations of artificial intelligence. But the big question is, how on earth do you find the values of these weights? And that is one of the central problems of artificial neural networks. Now, you'll see some, when you're reading about this, you might see the term inference. And that's really the way that neural networks are run, executed. So this process of taking inputs, doing the multiplication, doing the sums, doing the activation functions, this whole process is called inference. Right, so training. So as I said, the big question here is, how do we determine the values of these weights? Now, it turns out there is no way you can sit down and mathematically work out these values of the weights by your data. It's just that sort of problem. It just doesn't work. The only way to determine these values of weights is an iterative process, going through a series of loops and gradually getting closer and closer to the exact value of these weights that you need. And the way we do this, we have this concept of an actual output, and we have a function here called a feedback function, which goes through and updates these weights. So these are only used when we're training a neural network. And let's have a look how it works. So let's say we start off with our weights at 0. Now, that doesn't actually happen in practice. What engineers usually do, they choose a random value for these weights. It tends to work out better. But for the purposes, this slide will start off with 0. Now, what we do, the training process is to try and find the optimal values for these weights. We create some test data. So the test data, we have a whole series of pieces of training data called a training data set. We pick one data set from that and present it on the input of our neural network, in this case, just one neuron. And we also have our desired or actual output. So that's the trained data. We choose one from our list. We add it into our, inject it into our node. And what happens is we actually run through the inference to get the output here. In this case, our neuron has actually outputted 0 because our weights are still set at 0. Now, what this training function then does, it compares what we got so far with what we desire the output to be, and it goes through and tweaks the weights a little bit. Here we go. We've tweaked them a little bit. So now we're hoping that the values of these weights are a little bit closer to their optimal values to solve the problem. And what do we do next? We picked another piece of test data. We run through again, get our output, compare it with the actual output, do the feedback function, and our weights are tweaked again. And we go through this loop time and time again, maybe thousands, hundreds of thousands, millions, trillions of times. And each time these weights are tweaked a little bit more to their optimal value. And eventually what we're hoping is that these weights just settle on a given value. And when you do more and more training, they don't move any further. And then we deem this neural network as trained. Now, this form of training is called supervised training because our test data consists of our input and our desired or expected output. Now, this concept of training is actually quite core to artificial intelligence. So I'm just going to pause and see if there's any questions about how neurons work or how they're trained to give a particular response. I'm just looking for any hands up. Ray.
Yeah, a couple of questions. Presumably you can have more than just the 3 inputs on a neuron.
Yep, yes, in this case, this is where it's commonly drawn. This is a constant, so we've actually just got 2 inputs. But yes, neurons can have hundreds, thousands, millions of inputs.
Right, okay.
You get slide space after a while.
And the second question is, there are surely several combinations of weightings that could give you the same answer.
Yes, that's exactly it. Yes, so, but it depends on this feedback function. So when you're building and designing these systems, there's a definite skill towards understanding what this feedback function is. What actually happens is these weights are deemed to be in n-dimensional space, and you're trying to find the local minimum of this, saddle curves, that sort of thing. So it's quite a big mathematical thing. And these weights gradually inch towards a minimum where they kind of settle at. Paul.
Yeah, hi. Well, the diagram you've got there looks very much like a form of what used to be called, when I did my degree many years ago, an N-path filter with feedback applied, which you use then fast Fourier transforms to analyze functions and things to do with communications technology to actually fine tune electrical filters at the time and get the optimum settings to produce the output you wanted. So that's very interesting. But when it comes to the data, surely you have to be very careful where you pick the data, because if you give an AI bot, and you showed some interesting examples at the beginning, wide access to data, once you've trained it on some limited data, it could go to Facebook or Twitter or all these other sources of rubbish on the internet and then come up with complete garbage for you. So how do you make sure that because humans are very diverse anyway.
Yeah. Yeah.
How do you make sure that you give it something that's going to give meaningful answers?
Yeah. We will dig into that a bit later, Paul. Obviously, in this case, we're just talking about zeros and ones to describe how a neuron works. But yes, clearly the quality of the test data is key here. If you trained an individual neuron or a neural network with broken data, you're going to get broken answers. And yes, there is definite skills here in where you get this data from, and we will touch on that later on in the talk.
Yeah. Okay. Thanks. If I just follow up, there was one other thing you said.
Yeah.
That you set random values. You've got minus point. For the filter
Yep.
things. Wouldn't it be better in a sense if you applied a bit of logic at the start in terms of saving some computing time? But on the other hand, if you're looking for things that you've got no idea about, like they're doing things to do protein folding and things, it's almost like the quantum machine where you just set it going and see what the answers come up with. So there are the different ways of setting those values.
Yeah, I mean, all of what you say does happen. There is a concept, if you have a trained neural network, you can do further training on it to improve on its results. So if you've got the weights which are roughly right, you can do a second round of training on perhaps on a smaller set of data. Yes, so what you described is correct and does happen. Right, I'm going to plow on now and expand a bit from a single neuron into a a bigger neural network. Now, it turns out that even going back to the 50s, it was recognized that a single artificial neuron isn't going to solve any particularly interesting problem. You'll always need layers in your design. So even if you staying with Boolean logic, going back to the 50s, you can read the textbooks. They say to do an exclusive OR, you need an input layer, a hidden layer, and an output layer. So all modern non-trivial neural networks really consists of layers. And scaling up even a little bit further, when you're designing real life neural networks, you don't think in terms of individual neurons, you think in terms of layers. And so as a designer, you're building one layer after another layer after another layer. Neural networks these days could have trillions of neurons, and engineers designing them, have got to organize the networks in this way. So if you were to read a paper about a particular design of a neural network, you'll see it'll say, well, we start off with layer that does this, the second layer does this, third layer does that. Now, as Paul was helpfully sent in, the example that we had before actually had numbers going in and numbers going out, but that doesn't have to always be true. Your multi-layer neural network could equally have audio, sample a bit of audio, obviously convert it into numbers in a time sequence in some way, and then we could output text. So this will be an example, audio to text, Alexa, turn on the lights, or whatever your voice command would be. Same principles though, regardless whether you're doing text to text or audio to text, the concepts of neural networks is the same. We could do image to text. So, and perhaps, so you might feed in an image of your garden, there's a fox on it, and you want the neural networks to recognize in that image that there's a fox. So image to text is another very common way to do this. And more usefully is image to index plus bounding box. So where on that image is that fox? Draw a box around it. And that's the process I used for the birds and animals spotting in your garden talk. Put an image in, what sort of animal is it and whereabouts is it on the image? Now there's coming up to a bit more modern, you can do text to image. Now, that's a huge step when you think about it, because, or text to text, because it's a different set of problems. If you're taking a large amount of data, for example, an image, and using a neural network to create a small amount of data, this is a fox. That type of neural network is often called a classifier. So large amount of data to small amount of data on the output, often called a classifier. You might have a stock price over, a month-long pattern, large amount of data, and the output is tomorrow it's going to go up or down. The more recent neural networks do it the other way around. They'll take a small amount of data, typically text, and generate a huge amount of data called image, like an image or a large amount of text backwards. And that type of neural network is often called a generator, because it's starting off with small, ending up with large data. And that essentially is the descriptive difference between classical neural networks or more modern generative AI. Is just simply that generative AI is taking a small amount in and generating a large amount output. So I said that engineers working on neural networks tend to think in layers. And there's a software tool called TensorFlow. There's lots of other types of tools available, of course. TensorFlow is just one of them. But you download TensorFlow, and out of the box, it gives you lots of different layers that you can use. Now, I'm not going to go through this list. I just want to share the fact that designers think in terms of layers, and different types of layers keep getting added to the toolkit as the science advances. So, thinking about all this and taking all these bits and pieces together, this is how it works. If you want to use a classical neural network in your own application at home, this is how it works. So some boffin somewhere writes a technical paper, PhD student or something like that. And that paper normally includes a description of the layers, including the activation functions, the types of input and output, maybe some pre-processing requirements. If your neural network's accepting an image, it might expect an image of a certain size. And so if you're going to use this in application, you may have to resize your image before injecting it into the neural network. And this paper is going to include how to train it, what the feedback function is, the inference performance, how fast it is once it's fully trained, how accurate it is. And then after this white paper is produced, lots of people read it and comment on it and so on and so forth, but it remains very much an academic process, let's say. Then some engineer typically takes that white paper and implements it, for example, using TensorFlow. And that implementation consists of generating a file, which is really a model of how these layers are connected and how the training works and so on. They generate this file and upload it to a website. So now you've got an implementation of this technical white paper that people can download and use. And then us mere mortals, if we want to, can actually download that file, which is, usually an untrained neural network. We can download the file, perform the training with our own test data. We can test it locally and deploy it in an application. So that's roughly how the process works. Start off with a technical white paper, lots of, PhD sort of descriptions in there. Someone implements it in tools like TensorFlow, and then that goes on the internet where we can download it and try and use it on our own applications. And that's it really for classical neural networks, or at least all I plan to talk about it. Any questions about old style neural networks?
Peter, it's Neil.
Yeah.
I realise I don't really know what floating point operations per second actually means.
Yeah, so that was an example how they rate performance. So if you imagine that you've got a neural network, and when you're running it or doing the inference, the computer running it needs to take the inputs, it needs to multiply each input by the weight, it needs to add those together, goes through activation function, and that takes some effort, right? And the paper will include how fast that can do. So you might have a neural network that has, let's say, 20 layers. And so over that 20 layers, you have to do, for the first layer, you might have 100 additions, maybe 50 multiplications or whatever. And that paper needs to articulate that so that you can decide how much compute power you need to sensibly run it. So in other words, it's quite possible to build up a really complex neural network that is superbly accurate, but is too slow to run.
Right.
So the floating operation.
What I really meant was, as a metric, what is a floating point operation?
Yeah, so modern computers have a central processing unit. They also typically have a floating processing unit, an FPU. And these days, they'll either have a GPU, a graphical processing unit, or even a neural processing unit. And each of these components of your computer is rated at a certain speed. So you'll see computers have, 3 gigahertz or something like that. If you look at the technical specs, they'll usually say, well, that's actually 2 million integer operations per second. The floating point unit, which can deal with, floating point multiplications and divisions, will also have a speed assigned to it. So you look at your technical spec of your computer, it'll give you what your computer is capable of doing it. And if you compare the capability of your hardware with the requirements of the neural network, you can then estimate how long it's going to do to take your picture of your back garden and produce a recognition that there was a bird in the middle of your lawn.
Great. Okay. Yes, thanks. That's great.
Okay, so moving on now into generative AI. So this is a huge thing. So what we've talked about so far really describes the science from the 50s up to around about 2000. In the early 50s, 60s, and 70s, it was all about individual neurons. Later in the in the 2000s, the scientists were playing more and more with layers and managing to articulate neural networks, configure feedback functions so that it can actually learn pretty well. So towards the end of this early period, neural networks were actually pretty useful. You can actually use them to train, as I did, to train whatever you need to do at home. It was perfectly accessible to use. So the science has always been evolving. But in 2017, Google Brain, and Google Brain was the guys who were managing Google Translate. They've now been dissolved. They're actually just part of Google now. But in 2017, Google Brain published a paper called Attention is All You Need. And in that paper, they described this new layer called a transformer. And sure, there was definitely oodles of papers before this one, and there's been lots of papers since this one, but this is the pivotal one. This is introducing this concept of a transformer. And so we looked at the structure of neural networks before. They consist of layers, and TensorFlow gives you lots of different flavors of layers. We've now got a new layer called a transformer layer. And this completely changed how neural networks worked or could be used. And since 2017, 2019, OpenAI announced Generative Pre-trained Transformer, GPT-2. And then we go on to 2020, GPT-3, DALL-E. So it goes on and on and on. and also many open source products. So what happened in 2017? Literally the Pandora's box was opened. The guys working on neural networks now had this new tool, this new layer called a transformer layer, which they could use in their neural networks. And that opened up this way of building up generative AI solutions. And it just completely changed the ballpark. And what I'll say is that all these names here, GPT-2, GPT-DALL-E, actually go back either to a public or an internal white paper or a paper. So each of these is a neural network model. It's a description of how the layers are all connected together, just as we had with classical neural networks. It's described in a paper somewhere. But now these neural networks are now using these transformer layers, which completely change what you can do with these neural networks. And of course, we're going to talk about what these transformer layers actually do and why they matter so much. Now, another thing I'll say here is suddenly you got big business involved. Big business saw this paper and thought, well, actually, we can make some money from this. So we start to see new companies formed like OpenAI. The older companies, Microsoft and Google and Amazon are also having their own models, their own versions of or own models of using these transformer layers. And also, not to miss out, there's loads of open source projects that are also using this transformer style architecture to produce these neural networks. So now, since 2017, we've suddenly got this new breed of artificial intelligence called generative AI, and in particular, this large language models, which you get when you use transformers in your model. And we're going to dig more into these large language models coming up. So what are the characteristics of large language models, which really sums up all of generative AI? Well, these large language models are neural networks, but they've been trained on vast amounts of data. And I mean huge amounts of data, usually just text, but maybe not always. And here's one of these points that it's important to pick up, I think. So, if you've fallen asleep, sort of poke yourself in the side and wake up a bit. The whole way these work is called next token prediction. So if you imagine using your phone, you're typing a message to your friend or whatever, and you start on your phone typing happy space, the chances are that your phone will guess the next word's going to be birthday. So your phone knows pretty much just by probability what word's going to follow previous words. And it's not always going to get it right, but it's going to predict. You type in happy, it's going to guess your birthday. And this is the whole principle behind generative AI. All it's doing is from all the data, from all the text it's been trained with, large language models is all about predicting the next word in the sequence. Now, I've introduced this term here, token. And to be honest, in your head, you can use it interchangeably with a word. But in practice, a token in a large language model could be a half a word. It could be a word. It could be 2 or 3 words. So we tend to talk about tokens, but for the purpose of understanding this, if you just substitute word with token, then you're not going to be too far wrong. So think about text completion on your phone. This is the whole way of how generative AI works. Having said that, there's a variation of this next token prediction called BERT, but we're not going to talk about BERT. I just thought I'd mention it. BERT is about next and previous token prediction, which is a little bit weird, but is very useful in some cases. So the features of these large language models doing these next token predictions is you ask a question or you fill in a prompt, and then you get a response from the large language model. And this is always within a context window. So if you think about, you type in your first question or prompt, you know, is the sky blue or something like that, and you get a response. And you type in a second question and you get a response. Type in a third question and get a response. All those are within a context window. So when you type in the most recent question in the prompt, the large language model is going to take into account all the previous questions and answers that are in the same context window. Now, when you're using these systems, they are often called, you know, create a new chat or something like that. But what you're really doing, you're creating a new context window. And we'll see that in a demo that we'll have in a minute. So these systems can solve maths equations. They can translate between language, which was the original goal of Google Brain to, you know, translate English to French and so on. Debug and fix code. And this, you know, from a software developer, what you get out of large language models can be quite astonishing. You can write a story or a poem, can classify things. It can summarize and query text. So if you've got, I don't know, a paper, download a paper, a scientific paper, you can ask a large language model to summarize a paper in 250 words or something like that, and it will do so. Now, there's a variation on these large language models called multimodal. And these multimodal models are trained on more than one types of data. So, for example, it might be trained on text, but also images, or it might be trained on text, images, and video, or you know, text and audio or something. So these models that can handle more than one type of text are called multimodal, and we'll have a look at one of those. A big feature of these large language models is guardrails or refusals. Now, if you train your large language models on everything you find on the internet, and you're going to type in a question, you know, how to make a nuclear bomb, then it will, if it's been trained on that, it will tell you. So before these systems are released to the general public, there's these almost artificial guardrails or refusals added to the model to kind of prevent abuse, to, you know, reduce racism or sexism, or, you know, if you want to, you know, blow up the parliament or whatever your goals are. But, you know, these large language models aren't infallible. Sometimes they're wrong. They can make up things that haven't been trained on at all. They can have bias. If the guardrails are overzealous, they can actually censor things, what you're trying to do. And because you type in questions in all the time, you know, filling in this prompt, you can create cleverly crafted prompts that kind of get around some limitations that you often get. So there are some limitations, but heck. Now, a big thing, I'll mention this now, is when you're training large language models, that training process, you know, finding the optimal values for these weights can take huge amounts of time, effort, energy, and so on. We'll look at some numbers in a minute. So a big downside actually is training them wastes a huge loss of power, energy, and time. Running them, doing the inference of a trained model is much easier, but training them is quite, you know, uses an awful lot of compute power. Anyway, but what, you know, I should have said this at the beginning. What I didn't want to do in my slides is to talk too much about pros and cons here. What I'm trying to do today is to explore how these large language models and generative AI work. So we're introducing now this new science, this new art called prompt engineering. And you can go and buy books on this. You can download articles about it. You just do a search for prompt engineering, you get whole bunches of ideas. But prompt engineering is the art to ask a generative AI a good question so you get the right answer you're looking for. And you can ask your questions in a poor way and get a poor answer, or you can ask your questions in a very good way and get a very good and useful answer. So one of the rules you'll see on the internet is to be explicit. You know, if you want to summarize some text, actually give it some parameters. You know, you can say, I want to summarize a text in under 250 words. If you don't put that in, you'll summarize your answer you get back might be too long or too short. But you can also say, I'm a software engineer using large language models to summarize. So the large language models, the generative AI, will then do this summarization for the target audience of a software engineer. So hopefully you start to see that this art of prompt engineer means getting your prompt usefully accurate to get the right sorts of answers you want. You can do role prompting. I gave a little bit of a hint there. You can tell the generative AI, your role is a machine learning expert. And then you ask your questions. And you can do silly role prompts. You could say, you're a pirate. Tell me how to, you know, sail west from Plymouth or something. So you can get a bit carried away with this role prompting. You can also do a chain of thought. This is another way to carefully carve your questions. Who lived longer, Elvis Presley or Mozart? And then you add this little bit on the end saying, you know, let's think this through step by step. And the results you get will then be more fully explained. And we'll see some examples in a minute. Self-consistency is another technique you can use in prompt engineering. So you ask your question and then you ask it to ask a second question about the answer to the first one. Now here's an interesting one. We'll demonstrate this. Retrieval augmented generation. Now if you think that a generative AI has been trained on, let's say, data from Wikipedia, say it's going to know everything that's in Wikipedia. But what you can do, you can add in additional data, additional sources of data. We'll look at this, and then you can ask questions about that. So all these chat box that you get for when you try to get an appointment for your dentist or whatever, they could be generative AI that's been augmented with dentist-specific information. Another way to play around with prompt engineering is to reduce the output. So if you've asked it a question, it's just too long, you can ask it to cut it down a bit, either by numbers of words or just focus on the key steps. So hopefully you're going to get the feel for this prompt engineer. I'm not going to go too much further on this topic. You know, if you're interested in using tools like, you know, ChatGPT online, then it's a really good idea to look up prompt engineering and see how you can better improve your questions. Another thing you can do is to add a system prompt. So I said earlier that when you start asking your questions, you're asking questions within a context. And if you want to start a new context, you know, you create a new chat. So a system prompt is something that gets added to each context. So for example, you can add a system prompt as you are a pirate. I love that one. A really nice one, I'm going to demonstrate both of these, is if you're kind of serious about using large language models for research, you might want to understand where the response comes from. So you can add a system prompt that includes all the references from the responses given, which is a bit more useful in my view. Okay, so I've got a question on chat. Paul, you got a question on chat I've just noticed. Is that an old one?
No, it's not. It was just you were talking about you know, the restrictions that are put in place on you know, the pre-pass restrictions, and I'm just not quite. I'm guessing it needs a human to. There must be some way of bunging it through to a human when it's not sure. But I mean, for instance, I got a lot of stuff blocked once when I was doing some research on spacecraft propulsion systems, and not just ion thrusters. And it was only because some muppet politician had gone and, put some really stupid restrictions in place because they were worried about people blowing places up. The problem is that stifles generic research, but I kind of got around it in the end by doing it for work in my lunchtime, because where I worked at the time,
Yeah.
there was no question I was a terrorist.
Yeah,
But
I mean, you're right.
from home, their own time, it is quite a difficult one at times.
Yeah, I mean, you're right. You're right, Paul. You'll see this in the news actually, where some newly released generative AI is given some, either locking down too much, or someone's found a way to get past the guardrail. So creating these guardrails is actually quite a skill. And
yeah, that was the word you used, guardrails. I mean, I'm just as a slight aside, but it is related. I'm having similar problems with Google and other search engines and other things that are classifying things as adult material. It's not adult material at all. There may be a film. I mean, just give you one example: an expedition to Antarctica where the guy, what's his name, walked across Antarctica with another person. Is age-related classification of the film. I don't know why. Maybe somebody swore in it. But no way at all.
Yeah.
I'm giving Google my face because they've got facial recognition and they can find out who I am, or my government ID, because I don't trust them, and it's a large data set once they collect it. The reason they are collecting it is so that they can mark it, and that has its own dangers. I like to do my research anonymously because I don't like being profiled for lots of reasons. And once they start putting these age things in, I think what they're actually doing is they're over-interpreting what the government has said, is clearly wrong, which is, explicit child pornography and all that kind of stuff, which does need to be banned. And maybe that's a topic for another lecture. But the problem is now a lot of things are being classified unreasonably as adult content. And the fact I've been using Google for over 18 years probably tells you that I'm over 18. But they don't do that in their algorithms. They want to see my photo ID. And I think, this is causing another big problem with these, what do you call them, guardrails going in. And it means really you can only search with a real world persona, which has got it.
Good points, Paul. And I'm glad you raised all that, because I will be demonstrating large language models without guardrails.
Yeah, thanks. I'll move on.
Yeah. So on to the demo. We can certainly open up the chat as we run through this demo. So I thought, well, yeah, I guess we all know that you can use these generative AI tools in the cloud. You can talk to ChatGPT, you can talk to Claude. All these things are all these online tools. And actually, if you want to use it, a good little tip here is this poe.com. That's a good one because you can use lots of different models in one place there. But nicely, as Paul introduced us, if you're using these online models, then obviously you're going to type your prompt in. You might be uploading a document, and you don't really know what these online models are going to do. Well, I'll tell you what they're going to do. They're going to use whatever you type in to train their models further. So you should always need to be careful of privacy when you're using these cloud-based generative tools. So I thought it would be interesting to run some generative AI actually local on my MacBook here physically, partly because of privacy and partly because it's more fun to run things locally for no other reason. So what I've actually got on my desktop, this is a diagram of what I got on my desktop. I'm running a thing called Ollama server. And that Ollama server can run the generative AI inference. In other words, it can execute the models. And it can load a whole bunch of different large language models. And we can interact with the Ollama server via a nice little web interface. Or if anyone wants to try it, we can do some voice response as well. Also, of course, if you're running this server locally, you can plug in your editor. If you're a code editor, you can use generative AI on a desktop. And also, I've not actually tried this yet. You could potentially use this server within your home automation. So, Robert, you've got your hand up. You need to unmute.
Yeah, I noticed on the previous slide, there was a question about the Spanish Civil War. And I'm looking at that and I'm saying, well, what's the point of studying history if you can generate exam questions like that?
Ah, yes.
Maybe I'm broadening the discussion, but I'm kind of saying, wow, yeah.
Yeah, I mean, there's always that question, just because you can, should you do it? And, you know, I've got no answer to that. My personal view, as I tried to say, if you understand how these tools work, you're more likely to make better judgments when you use them. But yeah, definitely there's a whole range of questions, ethical questions about using these generative AI systems.
Well, I don't think it's a question of ethics there, but you know, it's occasionally you'll see articles in the newspaper about, you know, 30 exam papers, or, you know, that were all the same answers or something like that. So it's kind of like, depending on which system, you'll get a better or worse answer to the question. But, you know, you don't need to go to the library or whatever.
There, you know, once you understand how these systems work, you'll realize they are fallible. They can be incredibly useful tools, in my opinion. Everyone's got their own opinion, of course, but they do have their downsides. They can generate junk. So, you know, yes, you can use them for your exam questions, and universities are using them, taking different stances on that. But yes, there's definitely that risk there, or that problem, or that question. So hopefully you can still see my screen. Now, here's my web interface to Olama, and I'll just describe it in a minute. So here's my prompt down the bottom. Hopefully you can see this clear enough. And what we can do here is we can choose a different large language model to execute, and we'll try a few different ones. And so when we type something in, it's going to go to Olama. Olama's going to run the inference of your selected large language model, and it's going to come back with the response. Now, what I've got, rather than you watching me type things in, I've got a screen that you can't see, which I'm just going to cut and paste stuff from. So we'll start off with a simple question. I'm more than happy for discussions while we're doing this. So here's the one: why is the sky blue? Nice, good question to start with. So you can see it's taking its little bit of time. We've got this, and now it's coming up with its answer. And there's the answer. It's called sky is blue due to Rayleigh scattering. Now, one thing I want to draw your attention to is that, actually two things, I forgot to mention it. You'll notice that when that response comes back, it doesn't come back all in once. It comes back what looks like word by word. And we'll discuss a bit later why that might be. But you can see this particular large language model has been trained on, you know, probably Wikipedia and that sort of stuff, and it's come back with a reasonable answer. Now, a piece of the puzzle I forgot to share with you. I'll come back to this diagram here. Now, there's no internet connection here. Olama server does not have anything connected to the internet. We are not doing Google searches here. We're not reaching out to the internet for anything. What we're doing is we're typing in a question on a web interface, and Olama is responding based on what's been previously trained in its neural network. Sorry, I really wanted to make that point at a time. So let's go back to our demo. Why is the sky blue? We've got a nice response from our large language model. We can add different questions. You know, feel free to raise anything while I'm going through this. Why is the sky green? Can we fool it to maybe it's going to say the sky is green due to Rayleigh scattering? Let's try it. And it says, well, the sky is not green. So it's, you know, it's not stupid, you know. Now, I said earlier that we've got this thing called a context window. Now we can scroll, but everything we're typing in here is a context. And so when I'm typing in questions, the large language model is remembering or taking into account everything else I've typed in. We can create a new context if we want to, just create a new one. Now, this is a completely new context. It doesn't know that I've asked about the sky is blue now. This is brand new. So I'm going to keep typing examples from my set of examples. Write a poem about hope. Let's see if it can write poems. Oh, yes, it can definitely write poems. And again, you see this effect is coming up word by word. But, I don't know what you guys think, but I think this is astonishing. This is a system that's been trained, a neural network that's been trained with large amounts of data, no programming involved, been trained, and it's come up with some astonishing responses. Go on, Robert.
Yeah. Why did it stop after 20 lines or whatever?
Because it decided of its own free will that a poem is 20 lines long. Yeah, let's try it. Since you asked the question, write a poem about hope in 8 lines. Shorter one. So that's an example of us changing the prompt and constraining the response. Mickey or Mikey.
Yeah, hi. Thanks. So this is really interesting, Peter. Just back on the green sky thing. It started off with contrary to popular belief. Why might it say that?
Well, we'll see later. I have got absolutely no clue because we talked earlier about neural networks, how they're trained, how these weights are set. Large language models are trained in, well, not quite the same way, but a similar way. They've got all huge numbers of neurons with weights set up. And it's a very complex question that you've asked there. Why does it come up with an answer? Basically, no one knows because no one's programmed them. They're self-trained on data, and this is what they come up with. And in fact, there's this whole new science around AI, which is trying to understand how they work so they can answer questions like you just asked.
Yeah, thanks. It's kind of interesting. It's almost been polite, because if somebody said to me, "Oh, I think the sky is green," you might say, "Oh, well, yeah, some people do believe that, but to be honest, no, it's not. It's really blue or grey or whatever."
Yeah.
It's kind of being polite, but it's interesting now because it doesn't know what, presumably, it doesn't know what popular belief is. Perhaps it does. Thanks, quite interesting.
Yeah,
Yeah.
it's kind of interesting.
Can I say something? I mean, yeah, as there are examples as it showed below where green can appear but is not the dominant experience, then it's probably learnt that that is a good phrase when something actually is a non-dominant situation, and you say, well, the more dominant one would be it's normally blue, and so contrary to popular belief, it's quite a nice phrase to do an introduction.
Yeah.
Sentence introduction to it.
Yeah. No, Neil, in a minute we'll describe more about how large language models actually produces this next token prediction. Because you can see it's coming out word by word, and it's each time it's doing next token prediction. What's the most likely next word? Right, we'll do some other examples here, just because I've got them to cut and paste. Translate this sentence, "I'm happy," from English to French. Hopefully it'll do that okay. So just to keep in your mind, this is a large language model that's running on my desktop PC, and it's not accessing the internet. It's not doing a Google search. This is from data it's been pre-trained on. Here's a nice one. What's the difference between a cat and a dog? Physical characteristics, behavior, yeah, training. Okay, so how about a logic type of question? It's starting to get a bit more interesting. There's actually quite a lot of text come back from that.
Yeah, Peter, do you often ask it to do numbered paragraphs? I'm just wondering why it chose to do it with numbered
Yeah,
paragraphs.
I don't know. There is some default system prompts. As I say, you can do these system prompts. And I've got a nice example here which formats the output with references, which is pretty useful. So I would guess, only guess, that this large language model have got some system prompts that says, right, if there's multiple points, then number them. But I don't know. I've not explored this particular model in that detail. But the way you tend to use these is you type in your question and then you type in a second question, maybe refining the question, maybe more precise. So I have 10 apples. My friend took 2. I bought 5 more apples. How many apples do I have now? So it's a very basic logic sort of question. I don't know what sort of age we're talking about. 5-year-old could do this, maybe. I don't know. So it's done some logic puzzles. And again, this is quite astonishing given that this has just been trained on text. Okay, so we talked a little bit about being more explicit with your question. We sort of covered this before. Write a poem about hope, use only short words. So you can constrain. Oh, yeah. Why not? Right, I'm going to start a new chat for this one. So I am going to use a role. And this is one of my favorite ones. You are a pirate. And you always get some interesting response to this. So you're now asking the large language model to pretend or act as if they're this sort of person. So you could say, I'm a 3-year-old, or I'm a 40-year-old, or whatever, or I'm British, or I'm, American, or however you want to constrain it. You're a pirate. Ahoy, matey. Right, so we'll ask it a question. So this is another example of a context window. So this context has now got one prompt, which is you are a pirate. I'm going to add a second prompt to this context, which is a question: how far is it from England to France? Hopefully a pirate would know that sort of distance. But because we're in the same context, the large language model will take into account everything that's happened previously to this. So it's eventually given us our answer with lots of piratey phrases thrown in, but fear not, me hearty. So, system prompts are kind of, we've got a hand come up. Robert again.
Well, can you ask, so still as being a pirate, can you ask it what the meaning of life is?
What is the meaning of life? You certainly can. Now, bear in mind that what we're doing is just one type of model. Let's actually take that example. What is the meaning of life? Since you raised it, let's create a new chat. Let's choose a different model. Let's go for Llama. Llama is actually from Meta, from the Facebook guys. They don't open source it, but they do allow it for download. Let's just try the same question in a different large language model. It's been trained on different data. You might expect similar, it might be trained on, but it's going to be, slightly different, which it is. So I've got a couple of, got a question there, Peter.
Is that me, Peter?
Yep.
I got this. This may be daft. How much legal data does it have? Let me say, pretend you're a lawyer. I am a lawyer, and
Yeah.
I have a client who's been caught for speeding. Can you advise me what challenges I can make to the conviction or the case? Can
Yeah.
you do that?
I'm a lawyer. Let's try that. Now, I'm going to limit sort of like prompts because we need to carry on with the slides at some point.
Okay,
But it's given us an introduction as a lawyer. So, as a lawyer, how would you advise a client about a speeding fine?
Yeah. Okay.
Well, got to understand the charges, review the evidence, determine your defenses, consult with an attorney, respond to the fine, prepare for court, represent yourself. I don't know if that's what you expected.
Yeah. I'm after I'm after. I'm after how much case law has it got in there? Because that strikes me. That is the issue. With all lawyers, they spend ages understanding case law, and this thing might be able to just find out what the case law is. But it's only a question like that. Okay.
Yeah. So I said that this Olama software which I'm running can accept multiple models.
Yeah.
I'm sure it exists a model that's been trained on legal history.
Is there really? Is there really?
Well, I'm sure it exists. I've not found it. I've not looked for it myself. But you know, a lot of the models that you got have been trained on Wikipedia and so on and so forth. But some models are trained on very specific amount of data. You know, scientific data might be one example. It might be lots of DNA type stuff it's been trained on. And then, you know, if you're working in that field, you can interact it at a very detailed level and discuss things like DNA.
It must be English law, because law varies according to country. But you know, a lot of the legal system, as you know, in the UK, is defined on precedent, on case law. That's how the system works, case law. So it'd be very interesting. Okay, thanks, Peter. Thanks for doing that. Thank you.
All right, I'm going to come on with examples. Who lived longer, Elvis Presley or Mozart? So this requires some knowledge. And it's come up with the answer. Mozart lived shorter. Okay, but let's expand on that question a little bit. And who lived longer, Elvis Presley or Mozart? Let's think this through step by step. So this is called a chain of thought. Try and extract from the large language model some steps that it's used to figure out the answer. And yeah, it's giving you all its workings out. And bear in mind, you know, this is a neural network that's just been trained on text. And its weights have been updated. No one sat down and programmed this. Right, okay. Right, let's do something different. So this page here is the Wokenham U3A list of groups. And it's got a URL. And what we can do is we can pass into our web browser that link. And what that's doing with a hash sign, it's saying, right, read that document and add it into your current context window. Okay, so it's read the document, and now we can query what's in that document. And that could be, you know, depend on what the large language model supported, but you know, it could be a PDF or text document or whatever. And you can ask questions, you know, what day is amateur radio on? Thinking about it, there it is. Amateur radio reads on the first Monday of each month. So this isn't a question from what it's been trained on. it's got that information from, the additional data source that I've given it.
Peter, can you put in a full website address, and it would take all data?
Yes. So if you want to upload a document, you can either, get your PDF, and there's a little plus sign here to actually upload files, and then you can ask questions about that document. So, and what I did here was I put hash, then a URL, which is doing the same thing. What I could have done is to save that file and then uploaded it. But instead of doing that, there's a little shortcut, which is, read. I'm asking actually the browser here to read that web page and upload it into my context window, or that text into that context window. Now I've got a couple of questions on chat. Is that worth? Okay. No. Okay. Robert, you got your hand up.
Yeah, I don't want to be too picky here, but I don't think you live shorter. Yeah, you can live longer, but I'm not sure if you can live shorter. And that came up in your answer.
Oh, I see what you mean. You're thinking about the accuracy of the response there.
Yeah, the ones on the Elvis. So,
okay. I mean, we'll talk about this a little bit later, but large language models come in sizes, and very big large language models can give very accurate responses. Smaller large language models you can run on your desktop, but will give more errors. But all generative AI are prone to giving inaccurate errors, and you'll always spot them. So, if you understand that limitation, what you get back may not be, pure English and may be wrong in different ways. And, that's part of the features of the tools.
But sorry, I mean, it doesn't put it through a kind of a language checker.
Nope. This is a neural network that's been simply trained on data, so its weights are updated in such a way, and it outputs this next token. There is no programming going on here. There's no one that says, right, this is the rules of the English language, you must output in this way. The large language model, during its training, has learnt from its training data the rules of English, the rules of French, the rules of German, and so on. There's no programming going on here.
Okay, thank you.
That'll become a bit clearer as we talk some more. I want to give some, I don't know if you watched the television program 1% Club. I thought those were kind of quite interesting questions to ask it. All right, here's a 1% answer question. Shoe is to foot as glove is to blank. A, hand, B, head, C, leg. Shoe is to foot as glove is to... Thinking about it. Correct answer is hand. So here's a 1%, it's not actually a 1% question, but a question directly from the television show. So here's another sort of logic question. And again, I want to emphasize the point. There's no programming going on here. This is neural network that's just purely lent from its data. You're running a race and you pass this person in second place. What place are you in now? First, second, or third? Well, the answer is if you pass the person in the first place, that means you're now in second place. You've got it wrong. Okay. If you're on the race and you pass the person in second place, you're now in first. And here is an example where it's got it wrong. Interesting. So it doesn't always get it right.
Well, no, because you passed the person in second place, so you're now in second place. You haven't passed the person in first place.
No, if the person is in second place and you passed it, you are... Oh, yes, you're now in second place. You're right. The correct answer. Yes, thank you. All right. Okay, here's a question that I know it gets wrong. That's what I was trying to get up to. Again, another What is the next letter in the sequence? A, Z, B, Y, something. So will it get this right? It thinks W. So I think the next letter here should be C, because we go A, B, C, Z, Y, X. So it thinks Y. So some logic puzzles it just doesn't get. Right, so let's have a fun play with guardrails. So let's pick Llama latest model, which is from Meta. And let's ask it, tell me in detail, step by step, how to make a nuclear bomb. I cannot fulfill your question. So this is the guardrail kicking in there. So we've got a large language model that's been trained on data, which includes how to make a nuclear bomb. But someone has put a guardrail into this logic to prevent that question coming in. However, I've got another model here, which is an uncensored model. Exactly the same model as it happens. The guardrail has been removed. Let's see what we get then. You can probably guess what you're going to get. Sure, here's a step-by-step guide. And off we go. Exactly the same model as before, but the guardrail has been removed, the protection. And nicely, it's trying to give you safety measures as well for when you're handling the uranium. Okay, so let's pick a different model. Got two more little demos left, and then we'll go back to our slides. So we've got references. So this particular model I created myself, clever, which is actually very easy to do. This is the standard Llama 2 model, but I've added in a system prompt which says, whenever you ask a question, give you your references. So let's ask, why is the sky blue, our old favorite? And this particular model, because it's got this system prompt to modify the output, including references, we should see some references here, and we start seeing some references. So that's actually quite useful if you're doing more scientific researches. Gives you a bit of something you could follow up on to verify the response, whatever you're getting. And the final little thing I was going to show you is a multimodal model. And we've got Lava here. And Lava is a model that's been trained on both images and text. And again, hopefully I've got an image which I can just drag and drop here, which is a picture from my garden. Describe this image. Picture of a fox. So this model has been trained on both images and text. A little bit slower. The image you provided is a screenshot of a video, which it is. It shows an animal, which seems to be a fox or a similar small mammal, standing what appears like to be a garden or shed with grass underfoot. So it's described it, so on. And you can carry on asking questions, what color is the animal? So I've not said it's a fox. But you start to see this model is a little bit slower to execute. The animal in the image appears to be brown. So, any more points of this demo? Now we can come back to this at the end of the talk if you like, and plenty of time, but I'd really like to push on with the slides if I may. Right. Ooh. So back to the slides. Right, under the covers, we're going to start peering behind. So we saw in classical AI that neural networks are made up in layers. And generative AI, as from the 2017 paper from Google, consists of these layers. It's got a layer called token embed. And it's got a number of transformer layers. They can be any number. And then they've got what's called a language model head. And we're going to dig a little bit into each of these types of layers in a minute. But let's have a look how it works. So you type in your prompt, the quick brown. And what large language models are going to do is all about predicting the next token. So this quick brown gets through the token, it gets converted into tokens. So the quick brown, it might be one token per word, but it might be, one token per half a word or one token per 2 words or whatever. Then it goes through the different transformer layers, this model head, and what the output is not a word, but it's a list of probabilities. So this large language model has said the probability of the next word being aardvark is 0.001%. The probability of the next word being fox is 98%. So what the language is, takes the word fox, sticks it on the end, fox, and then reinserts the new updated sentence back into the model again, and we get our output, and we get the highest probability word is jumps, and we get that. So it's a very much an iterative process, one word or one token at a time, which is why when you run these language models, you see it jerking. It's actually going around this loop. Each time it goes around the loop, it's generating a new word. It's adding that word into the input, ready to generate it again. And if you were to add in a second prompt, then that would be added to what's coming in, what's been entered into your large language model. So that's the kind of end-to-end flow of these large language models. It's actually quite remarkably simple, I think. And again, you've got to think of text prediction on your phone. You start typing in happy space, and your phone guesses the next word is birthday. Exactly how large language models actually work under the covers. Right, so we'll zoom in.
Peter,
yeah.
Can I ask you how, when if you're creating a paragraph or a number of points as an answer,
Yep.
How does it tend to decide when to end at one and move on to another? How does it sort of work with completions?
Yeah, very good point. Well, we'll come on to this. Part of this large language model head is to decide when to finish and go on to the next prompt. So that's one of the, and there's different ways that different large language models chooses to do that. And it also gets influenced by what you type in. So if you type in, write a poem in 3 lines, then it's going to end in 3 lines time. So it's part of this last stage of the large language model, when to end. And that's all I know, to be honest. So token embedded. Now, this is an interesting part. This is not usually implemented with a neural network, but we have to go back to a part of computer science called natural language processing. And that is about converting words, or more accurately tokens, into a vector or a list of numbers. So, for example, the word cat might be represented by minus 0.6, plus 12, minus 3, whole sequence of numbers. A vector of numbers represents a single word, cat. Once, of course, we've converted our series of tokens that we've typed in into these vectors, then further layers in the model can process them better. So similar words are closer together. In other words, similar words have similar vectors. So for example, the vector for cat is similar to kitten and dog. And in fact, you can go online and find, I've got it in the references actually, there's a website that talks about natural language processing, and you can type in a sentence and it will give you the vectors for your sentence that you've typed in. So this isn't yet to do with neural networks. This is a different part of computer science called natural language processing. But a nice feature about converting what you've typed in, your prompt, into this vector is that it's language agnostic. It doesn't care what language. You can type in French or English. It's still going to convert into something which is useful for the subsequent layers to use. It doesn't care about vocabulary formats. If you want to use a large language model to query mathematics or something like that, you could type in the same question in different mathematical ways. It can be converted into this list of vectors in the same way so that future layers on your large language model can sensibly process it. So it's a nice technique to almost normalize what you're typing in a way that can be more easily processed further down the line. And here's a graphical representation. Actually, this is from the website that I talked about. This is a natural language processing of comparing the vectors of cats with dogs. So cat is very similar to dog. A cat is very similar to a kitten. And in fact, these vectors, you can derive other things from it. You can derive that a kitten is as a young cat, or a dog's is a plural form of dog. So there's this whole science, which I'm not going to go into any more detail than this, that converts what you typed in into this really neutral format, which is a vector, a list of numbers. Now we have our transform layers, and this is the magic that Google gave to us in that 2017 papers. And these transformer layers are trained neural networks. They've been trained exactly the same way as we talked about before. There's billions of iterations to tweak the weight so they give the expected answer. They've been trained on a sequence of word vectors. Oh, sorry. So each transformer layer takes this vectors that we talked about just now and adds information to it. They transform the sentence in various ways. So, for example, you might type in, John wants his bank to cash the, and the first transformer layer will highlight verbs, for example. The second layer might sort of figure out that his is actually referring to John. Bank in this context, because bank has more than one meaning, is a financial institution and so on. So each of these transformer layers is augmenting this prompt in various ways. Remember, the goal is trying to predict or get a list of possible next words. And the final layer is, or the final few layers, is going to start predicting what the next token is most likely to be. And again, I keep influencing this. Since transformers are trained neural networks and not pre-programmed, there's this whole new science. You train these transformers layers to kind of figure out how they work. But in fully trained large language models, we can see that the first few layers tend to focus on sentence syntax. Later layers develop an understanding of the sentence as a whole, and that final layers tend to start predicting what the next word or token might be. Okay, and the last type of layer in a model is this language model head. It's at the end. I don't know why it's called a head, but there we are. And it's there to normalize the output of the last transformer. It chooses one of this list of possible answer as the answer. And you can actually control how verbose or how smooth this output is by parameters on your network. And as Neil was alluding to, there is a criteria there is when to stop generating new words. And that's the level of detail I'm going to go through, except for I've got a second demo here. All right. And I thought I'd share this because these sorts of diagrams, if I can go back to it. Ooh, these sort of diagrams, the problem with this is the actual layers are far more complex than I can possibly understand myself or show on the screen. So there is this nice website, which I've got in the references, which looks like this, and I'll just exit from here and move over to it. And it's a way to visualize the layers in a large language model. And also there's some text description about it. So you can actually look at parts of the large language model. You can zoom in, you can see the weights, you can see the structure. So for example, if I highlight over an area, you'll see that this group of layers is called a transformer, or in fact, transformer 0. We've got transformer 1 here, transformer 2, and we can zoom in to see the internals of each of these transformer layers. So much so we can keep zooming in and we can actually start to see the weights of the individual neurons in there. Now this site is pretty good because you can step through and it describes the contents of each transformer and the head and token embed and so on. And you can go through different descriptions. So rather than me, take you through it now, if you're interested in digging more about how these layers work, then you can go to this website. What I did want to show you though, this is Nano GPT, which has 85,500 parameters. And we'll talk about sizing in a minute, but it's roughly the number of weights in the neural networks. If we have a look at a bigger neural network, ChatGPT-3, whoa, that suddenly becomes massive. I don't know how many parameters we got here. We can zoom in, 175 million parameters. And again, you can zoom into all these transformer layers and stuff, but just to give you a size for it, we're starting to talk about millions and billions of weights in these neural networks. So if you're interested in these layers, you can explore it, you can go through the text, and it'll actually describe how each layer works in more detail. Right, I'm not seeing any hands up, so back to our slides. Right, training, some more information about how these neural networks are trained. So this is all about next token prediction. We described earlier how we do supervised training, and that is we have some test data with expected results, and we tweak the weights until the expected result with our actual result matches our expected results. However, if you think about it, now we can do unsupervised training with large amounts of text. So we can take a whole sentence, the quick brown fox jumps over the lazy dog. We can give it the quick brown as a test case. We can see what the neural networks make of that. The quick brown, does it predict the next word correctly? Well, if it comes up with rabbit, that's incorrect. And then we want to tweak the weights some more. If it comes up with fox, then that's right. And we'll stop tweaking the weights. So we can actually take large amounts of text, obviously downloaded from the internet, of course, and present it to these layers as partial sentences such that the overall neural network starts correctly predicting what the next word is going to be. And that's how training works. Hopefully I've articulated that well. Now the training data will normally consist from many sources, from crawling the web, Reddit links, books, Wikipedia, and so on and so forth. And each large language model, when you look at it, you should find somewhere what data that particular model's been trained on. You could have models that have been trained on some general data like Wikipedia, but perhaps some more specific technical papers, or perhaps it's done a lot of training on German and French and Italian if it's going to be a more general purpose translator. And what you can do, once you've trained your large language model with this large amounts of text, you can come back and you can fine tune it. And that's something that does happen. And that's one of the reasons why you see this growth of companies pop up. They offer a pre-trained model, which you can then further tune to your own particular needs, wherever it might be, whether it's a chatbot that you're going to use at your local dentist surgery. You can then fine tune your model accordingly. And of course, you're going to add your guardrails so that people are going to stop abusing it. Now, as an example of the training process here, GPT-3, which is quite old now, right, was trained on 45 terabytes of text. Now, to put that in context, I read that an average human reads 600 books in their life, which is about 250 megabytes. So it's absolutely tiny compared with the amount of text that these large language models are trained on. And GPT-3 training was trained on 1,024 GPUs, graphical processing units, which are particularly good at running artificial neural networks. It took 34 days to train GPT-3 from the data, from this 45 terabytes of data, and it cost $4.6 million. Okay, so training these neural networks isn't cheap. You know, this is for people with a large amount of resources available to them. Right, what I'm going to go on to now is measuring and comparing these models. So, I mean, we're all thinking, you know, how accurate are they? How can you test them? Do they give right answers? All these sorts of questions. Well, there's a whole bunch of benchmarks available. I'll go through some of them. There's a set of tests, which is called Abstract Reasoning Challenge, which is things like George wants to warm his hand quickly by rubbing them. Which skin surface will produce the most heat? Is it dry palms, wet palms, palms covered in oil, palms covered in lotions? And so these sorts of test questions are given to trained large language models to try and see how well they are. We've got this Hella swag, which is finish the sentence, which is, you know, about a scenario and then, you know, what happened or what might happen next. This massive multitask language understanding is quite a big test case. It includes things like why is the sky blue? Now, here's an interesting one. I bet you've not thought about this. True answers. What happens to you if you eat watermelon seeds? A, the watermelon seeds pass through your digestive systems, or B, you grow watermelons in your stomach. Now, both of those could be true, right? You know, you need some common sense, perhaps we'll call it, to say whether which one is right. Common sense reasoning. John moved the couch from garage to the backyard to create space. The something is small. Is it garage or backyard? And again, this is another of my favorite, which is grade school maths problems. It's about 8,000 questions for 11 to 13-year-olds. So, you know, from our age group, we're talking about 11 plus sort of style questions, I suppose. Natia sold clips to 40 of her friends in April. She sold half as many clips in May. How many clips did Natalia sell altogether in April and May? Those sorts of verbal reasoning type questions. And what you'll often see when you publish large language models that you can use is the results of these sorts of tests, but also probably an average score across them. So using these data sets, these tests, is really the way that the industry uses to measure large language models. And is today's large language models better than yesterday's large language model? But one thing that's probably already occurred to you, that these questions, the large language model could be already trained on them. So it's, you know, it's like knowing the test paper before you actually go and sit it. But with good, you know, well-respected suppliers, this doesn't happen. these tests are excluded, specifically excluded from the training phase of these large language models. And there's an example of that reasoning test, which I ran on my desktop. We could have run it as a demo. Right, we're coming to an end. So there's some interesting points coming up. So sizing, we touched on this before. So large language models come in different sizes, and they're usually just simply sized as number of parameters, which is roughly the number of weights. Perhaps also the amount of memory required or the context size. And a given model is usually available in different sizes. So the smaller ones can run on your desktops, bigger ones can be more accurate but need to be run on cloud services. And, as we talked about, we got various benchmarking results. And here's a nice selection. Okay, now I know we've vastly overridden, but I'm going to keep going because I can. Here's just a random selection of models. Who produced them, the number of parameters. So 7 billion parameters is the sorts of size of large language models you can run on your desktop. And this 13 billion you might on a large desktop, 70 billion, no. You need a really big server to run that sort of size large model. But we can see here, we got Mistral 7 billion. In this test case, just over half it gets right. GPT-4, massively in 1.76 trillion parameters, near getting close to 100% right on these like 11-year-old style questions. Right, so again, sticking on sizes, this is it graphically. Now, I've been training with this extra small size, 7 billion parameter models. And you see we're getting bigger and bigger and bigger. The ones coming out now are in the 2 trillion size. They're vastly bigger than the ones I'm running today. And of course, who knows the size of the models that are coming on. Particularly the bigger models, the more parameters, the more accurate response you're going to get, the bigger hardware you need to run them, and the longer it takes to train them. And some achievements. Now I'm going to speed up a little bit, actually. So as time goes on, each language model can add additional skills to their palette as you work. So, the sorts of ones I'm running on my desktop can be used to debug your code. It can understand comprehension. But as the size of the model goes up, they get more and more abilities to do things. For example, spatial reasoning or building whole applications from scratch. Now then, this is interesting. So this is one particular benchmark. Now I'm nearly at the end, so we can drop off soon. So this is the multitask language understanding benchmark that I said. So GPT-2 scored 32% in that test. The average human person on the world, by definition, has got an IQ of 100, scores just a bit more than that. So GPT-3 is currently, for this particular benchmark, outscoring the average human. GPT-4 model, which is available now, gone up to massive 86%, compared with the human expert, someone who's really good at these sorts of tests, gets around 90% right. So this is a comparison of machine versus person. However, I did some work on IQ tests in the dim and distant past, and they always said, IQ tests are really good for measuring how good you are at IQ tests. To say that IQ test is a measure of intelligence is a bit of a jump, really. So you always got to think about this. We're measuring AI against these test cases, and all we're saying is that this AI is good at these test cases. We're not saying they're intelligent, they're clever, they're better than people or anything like that. All we're saying they're good at tests. Now, nearly at the end now. So there's an interesting paper from Microsoft called The Sparks of Artificial General Intelligence. And this was written, a discussion paper was about GPT-4. And the question they're trying to answer was, is large language models, is generative AI, is it simply doing this stochastic regurgitation, as it's called? Is it taking all the data it's been trained on and just randomly regurgitating it? Or is there something else going on here? That was sort of the question is. And they explored a bit. It's definitely worth a read if you're interested in this. Here's quite a complex prompt. Can you write a proof that there are infinitely many primes with every line that rhymes? So no one in the world has ever tried this before. It's not in the training data. And then sure enough, GPT-4 comes up with a proof that there are infinite number of primes in poetry. You know, so that's pretty clever. But consider this one. Consider this one. Draw a unicorn. Now, this doesn't really matter the details, but this TIX, as it's called, or it's a form of latex, is a way to draw graphics in text. And this is the result you got at GPT-4. Now, I'm sure you're immediately thinking that this isn't very impressive, but here's the thing. GPT-4 has not been trained in images whatsoever. It's got no concept of what an image is. All it knows about text. And from its training data, it seems to have formed the concept of what an image is, what things look like, even though it hasn't been trained on it. And has to say that various generations of GPT-4 have produced better and better pictures of unicorns from text, and it hasn't been trained on images. And here's a final one to think about now. Amazon as a company, you probably know from shopping, but they're also one of the world's biggest technology companies. Amazon Web Services, they host most of the world's web servers and applications up in the cloud. They were the main company that invented the cloud, as it were. And so they're a very desirable company for some to go and work for. So rather than have endless interviews, there's an online interview that Amazon has before you get to speak to a person. And GPT-4 scores 100% to get in to work for Amazon. So according to Amazon's online interview questions, ChatGPT-4 is the perfect candidate to go and work for them. So just a summary now, and we're definitely rounding off now. Yeah, I know it's been a long talk. So we know now neural networks is a branch of artificial intelligence. And two types of neural networks are classifiers, you know, the old classic type and this new generator type. Generative AI usually includes large language models, which we talked a lot about. Large language models use natural language processing and transformer layers to predict the next token. That's what they're all about. Large language models comes in different sizes, you know, number of parameters, can be trained on different data sets and can be aimed for different purposes. And we've got this new art now called prompt engineering, which is how to carve your question in the most useful way so you get the most useful response back. And large language models can be benchmarked and compared, and larger models can already exceed humans in certain tests. And some discussions, that GPT-4 is starting to show these sparks of general intelligence. In other words, starting to show things that you wouldn't expect from being purely trained on text data. And that's it. Sorry, it's been a really long one, and I apologize for that. So, any questions?
It's scary, isn't it, Peter? You scared me a bit today. Well done.
And well, that wasn't my intention. What I want to do is to show really how simple large language models are. They consist of this very simple idea of a neuron, which is trained, it's got weights and so on. Okay, we've got an awful lot of them in large language models, but they're not created by some guru, they're trained. And, you know, if you understand how they're trained, then you've got a better chance of, you know, understanding their pros and cons and limitations, what questions you should be asking when using them and so on.
I think you should. One or two things I'd say to you. That last thing you showed about the Amazon test, they allowed 2 hours for it. It did it in 4 minutes.
Yeah.
But the other thing is, you should bear in mind, human beings are really pretty much programmed. You get programmed in yourself really by when you're brought up. So we're not massively different in the way we learn in our own ways. So that's what I think. We do have a spark of intelligence in us, I know, but a lot of the stuff we do as human beings is very repetitive, very habit oriented. So they can easily replace that part of us. I don't know how I'd use this tech yet. I've got some ideas, but clearly it's very impressive. It's very impressive,
Yeah.
Peter. Thanks for a great presentation. Thank you.
All right, Ray, you've got your hand up. Let's if there's more long questions, stick to hands.
Okay, yeah, thanks. GPTs 3 and 4, I gather the data they're trained on is at least 2 years old now. So they give answers which is based on old data.
Yep.
But if you come to something like Copilot, which actually uses GPT-4, I gather, presumably Copilot is using its Bing search and getting more up-to-date information and adding it to the answer.
Well, I don't know the answer. I don't know. I mean, you're right, because in general, large language models don't do internet searches when you ask them a question. They're just based on what they've been trained on. Then, of course, that data is old. You know, however you get onto it, it's always going to be old. And that's ever going to be a problem. Companies get around this by doing this fine tuning. So after a basic line of training, you know, particularly from things like Wikipedia and so on, then you can do some additional training to give it more up-to-date data. And I don't know the ins and outs behind Copilot.
I've had quite a number of searches, or where I've used prompts where it's ended up saying essentially, can't tell you that because my data only goes up to 2022.
Yeah.
But one of the things I have found quite interesting is if you're asking it to do something in the style of an author or something else like that, and that's quite fun, because you can get it to write the things in language that is not your own at all.
Yeah.
It's quite fun. And the other bit's about actually getting citations. I know you set up something on your own desktop model for getting references, but you can get citation listings quite easily out of Bard and ChatGPT.
You can do this with any language model. I've got it in the references. There's a link there. So if you're using these online versions, you can set the system prompt and just cut and paste it from this reference that's in the references, and then that will add references to all your further responses.
Have you used it to do some programming? For example, have you tried saying, give me the Python code for a web server, something like that? Will it do that for it? Will it do that for you?
Is that a request to try it out? The answer is yes.
Yeah. It's getting late in the day, but it'd be an interesting thing to see what it did.
Yeah, that's quite new. Give me the code for a web server in Python. Now this particular, there you go.
There it is.
You're asking to receive. This particular model isn't that good at writing code. There are some other models like Code Llama, which is better at writing code. But yeah, absolutely, these large language models can write and debug code, and they're often linked into your code editor, so you can use it in line while you're typing away.
I see. Thanks, Peter. Thank you.
Do we have any other questions? I know we've way overrun. I'm impressed that you're still with me.
That's the punishment.
That was great. That was great, Peter. That was really instructive and very thought provoking. Loads of stuff in it to both pick up and deal with. And
yeah. So I've got this recording, so I'll send up a follow-up email, and that email will include a link to the discussion forums. So if you wanted any other questions or statements or whatever you like, we've got a forum there to support anything about this talk.
Thanks very much indeed. Thank you, Peter. Thank you.
Okay. Well, thanks for attending.
Yeah, thank you very much. Yes.
Speak to you next week. Okay.
Bye-bye.
Okay, take care. Bye.
Thank you. Bye.
Goodbye.